Now it's time to address Archimedes' principle and the story that's associated with this um, goes a little something like this. Now, this is possibly very largely apocryphal, okay? But we are reasonably certain that Archimedes was enlisted by a king to perform the following action. But the story goes that Archimedes was tapped by the king to solve a problem. The king had given a metalsmith a chunk of gold to fashion a crown, and when he got the crown back, he wasn't convinced that the crown was made of all of the gold that he gave the metalsmith, and he was worried that the metalsmith maybe used a lesser metal and then just plated it with gold and pocketed some of the gold for himself. So the king tasks Archimedes with figuring out whether the crown is pure gold or not. And the problem, of course, is that the crown is very oddly shaped. So there's no way to get a estimate of the volume of the crown very easily. Whereas if you could get an estimate of the crown, the volume of it anyway, then you could measure its volume or calculate its volume. You could put it on a scale and measure its mass, and you get the density. So Archimedes is pondering over this problem, pondering over the problem, and pondering over the problem, and he one night is taking a bath, and he sticks his leg in the water and notices that the bath water rises. And then when he pulls his leg out, the bath water decreases. And when he puts his entire body in the water, it rises even higher and it hits him. Okay? The volume of the water that's displaced must be equal to the volume of an object that's being submerged. Okay? And the amusing part of this story says that when he realized this, he ran out of his house, ran out into the street, shouting, I've Eureka, Eureka! I found it! I found it! And everybody in the town knew that he was an eccentric, so it really didn't disturb anybody or surprise anybody. But that's the story is that he was running stark naked through the town, shouting Eureka. The sad part of the story is that, at least as legend goes, the crown was not pure gold, and the metalsmith was arrested and executed for defrauding the king. But that apocryphal story aside, there's a deeper implication to this statement, okay? And this statement that the volume of your water displaced must equal the volume of your submerged object is not Archimedes' principle, okay? Archimedes' principle actually says something else. So let's think this through, and let's suppose that I have a container with some fluid in it, and that fluid has a density rho fluid. Okay? And I'm going to submerge an object in here. Think of something like a brick. Okay? And so, if I think about what's happening with this brick, okay, now number one, the brick has some mass and it has some volume, okay, so these are the mass and volume of the brick. Right? But if we take a snapshot of the brick, now, I mean, in most cases, a true concrete brick or cement brick or something like that is going to sink in most fluids, especially if that fluid is something like water. But even if we take a snapshot while the object is sinking, it doesn't really matter if it's sinking or not. This following kind of logic holds true for all time, right? Once your object is submerged, then first things first, at the top of your fluid, you have some initial pressure P naught. And then when the top of your object is submerged, some height, let's call it H1, there will be some pressure at the top, let's call that P1, and the bottom of your brick will be height H2, and it will experience a pressure P2. Okay? Now, from our previous considerations, we know that P1 must be larger than P2. Or I'm sorry, P2 must be larger than P1, rather. Okay? And we know that because P1 is equal to P naught plus rho GH, where rho is the density of the fluid, and P2 is equal to P naught plus rho fluid GH. This is 1 and this is 2. So if 2 is deeper than 1, if H2 is deeper than H1, then pressure 2 has to be larger than pressure 1. And so you get a pressure differential, right? So for example, if I think of the pressure pushing down P1 here and the pressure P2 pushing up here, I will get a pressure differential of something like this, maybe a little shorter than that. Okay, so delta P is the difference between P1 and P2. But I also have a surface area, A, okay? And so the force from the pressure at the top is equal to P1A, and the force at the bottom is equal to P2A. Right? And so what this essentially boils down to is you also have the weight of the object. Okay? So the net force acting on your object is equal to F2 minus F1 in the upward direction minus mg, where m is now the mass of the brick. And that will equal the mass of the brick times your acceleration. And so at this point, it depends on what is happening. If your brick is sinking, then MA will be negative. If it's suspended, then it'll be 0. If the buoyant force is larger than your weight, then your object will rise. Okay, but let's come back to Archimedes' principle. The buoyant force exerted on your submerged object is equal to the weight of the displaced fluid. So this difference in pressure forces is your buoyant force. Okay? So this force due to this pressure differential is your buoyant force. This is what's pushing up on your object. But what's causing that to happen? Right? What's causing that pressure differential? Well, the pressure differential comes from the pressure at the top versus the pressure at the bottom being different, but it's exacerbated by the fact that some of your fluid has been displaced. So that increases the overall pressure in your container and or rises, makes the level water rise. Okay? And so what that combines to do is that this volume of your submerged brick, let's put this in quotation marks, if submerged, then the volume of your brick equals the volume of your fluid that's displaced. But your fluid that's displaced also has a mass. And the mass of that fluid is going to equal the, the volume times the density, right? So the weight of the fluid that's displaced is equal to the volume of your fluid times the density of the fluid times G. Okay? So the weight of your fluid that's displaced is equal to this. So therefore, this must be equal to your buoyant force by Archimedes' principle. So if you know what the density of your fluid is and you can measure the volume that's displaced, you can calculate the buoyant force that's acting on your object. Okay? So here's Newton's law for Archimedes' principle. Okay? Here's Newton's second law for Archimedes' principle. Now, one very common example or one very common situation where these kinds of things are at play, if you've ever taken a beach ball and you blow up the beach ball and you try to push it under the water and then you let it go, you'll note very quickly that the beach ball is kind of launched upward. The reason for that is directly from this. Okay, so let's consider if I have a large swimming pool and a beach ball, and I've tried to submerge the beach ball underwater. Now, the mass of a beach ball is not very much. Might be a few hundred grams fully blown up. So let's just call it 100 grams. Okay, it'll at least be on that order. The radius of a beach ball might be something, like between 5 centimeters and 15 centimeters, depending on the size. So let's just call it 10. So the radius of the beach ball is going to be 10 centimeters. And let's just call, even though pool water is a little bit more dense than pure water, this will still even get the point across because the pool water is going to have an even larger buoyant force than pure water, but the buoyant force due to pure water is still going to be extremely large. So that'll still get the point across, right? So let's let the density of our fluid be 1,000 kilograms per cubic meter. Okay? So what is the buoyant force acting on the beach ball, right? And how does that compare to the weight of the beach ball? Whoop. F sub capital B is your buoyant force. We need WBB for beach ball. Question mark. right? So first things first, the weight of the beach ball is very easily computed. The weight of the beach ball is just the mass of the beach ball, 0.100 kilograms. Times gravity. Okay, so this is 0.98 newtons. So what's the buoyant force? So your buoyant force is equal to your volume of your displaced fluid times the density of your displaced fluid times gravity, right? And so the volume is going to equal the volume of your displaced fluid must equal the volume of your beach ball, because the volume of your beach ball is just pushing the water out of the way, so the water has to go somewhere else, right? And that will go into rising the level. And so we can calculate the volume of the beach ball to get the displaced fluid. So the volume of your beach ball is equal to 4/3 pi r cubed. So if I punch this in my calculator, what we will get is, if I take 4 divided by 3 times pi times 0.1 cubed, so 0.0001. Okay, so the total volume let me make sure that this is right. Yep. 0.04. So essentially 419 cubic meters. Okay. And so the density of our fluid is 1,000 kilograms per cubic meter. So the volume of our fluid is 4.19 times 10 to the negative 3 cubic meters. The density of our fluid is 1,000 kilograms per cubic meter. And we're also going to multiply that by 9.8 meters per second squared. So 4.19 times 10 to the negative third. 41.1. Okay. Now compare that. So if I look at the free body diagram of the beach ball here, right? If I draw a free body diagram of the beach ball, this is what it's going to look like. I'm going to have a buoyant force acting on the beach ball of 41.1 newtons and a weight of the beach ball of 0.98 newtons. So these arrows need to be a factor of 40 times different in length. Okay, so this is the weight of the beach ball, and this is the buoyant force. Okay, so this is why the beach ball immediately launches upward. Now, it doesn't necessarily launch out of the water very high, and you'll probably have noticed this, and this is due to the fluid resistivity of the water itself, right? It has to move through the water, and the water is very resistive to that. But if you could launch the beach ball with an equivalent force in air where it didn't have as much resistance, then you would absolutely see the beach ball launched quite high, right? So that's why the beach ball, when it's submerged, completely, it can be hard to keep it down as well. It can be hard to push a beach ball all the way under the water, and this is why the larger the beach ball, the more the buoyant force. And beach balls, a smaller beach ball is really not that much lighter than a larger beach ball, but the larger beach ball takes up a lot more volume and therefore is going to displace a lot more water, and that's going to increase the buoyant force even more. Okay, so if I were to increase the radius to say 15 centimeters so that I had a beach ball of 0.15 meters in radius, then I'm going to increase my buoyant force by the cube of that factor that was increased, right? Or essentially the cube of 33%. So, well, actually, in this case, the cube of 50%. So, it would go up substantially, even if the weight does not really go up all that much, right? So, that's why your beach ball launches upward, and it's just completely due to this idea that your buoyant force is equal to the weight of the fluid that's displaced, right? Now, there are three scenarios that you have when considering objects that you might place in a fluid. Number one, if the object does not fully submerge, i.e., if it floats, okay, then that means your buoyant force is larger than your weight, right? If the object becomes suspended in the fluid, then your buoyant force and your weight are equal, right? And if it sinks, then your buoyant force is much larger than your weight. And if you think about it, this should make some sense, because in the example that we just did, the buoyant force was much larger than the weight, and you actually had to push the beach ball down to get it underwater. Otherwise, it just floats on the top of the water. Very little of it is submerged under the water, right? But there's an interesting thing that happens here, okay? So if we consider a not quite fully submerged object, so let's think about scenario number one here. Let's suppose I have a tank, and that tank has some fluid in it, and I, submerge something. Maybe this is like a block of wood, if you will. Okay. So some of my object is submerged, and that object will displace an amount of fluid equal to that, right? So we have the volume of my submerged part is going to be equal to the volume of the fluid that's displaced. And but I also have the total volume of the object itself and the mass of the object. Okay? So we're technically going to have three volumes at play. The volume of your object, the volume of your submerged part, and the volume of the water that is displaced by the submerged part. Okay, so the logic goes like this. You can actually measure the density of your object if you know the density of your fluid via the following. Okay. So the fraction of your object that is submerged is going to equal the volume of your submerged part to the volume of your object. And if you think about it, that should make some sense. But because the volume of your submerged part must equal the volume of your fluid that's displaced, we can say that the volume of the fluid that's displaced, or this is equal to the volume of your fluid displaced over the volume of your object. Okay? And so the volume of your fluid is going to equal the mass of your fluid divided by its density divided by the mass of the object divided by the density of the object. Now here's the crucial point. What is the relationship between the mass of the fluid that's displaced and the mass of your object? Well, if you think about it, I've got the weight of my object pulling me down. Let's not use red since we've already used red. I've got the weight of my object pulling me down, which is equal to the mass of the object times g. But I also have the buoyant force. And the buoyant force is equal to the mass of the water that's displaced, or the mass of the fluid, whatever the fluid might be, times gravity. And here's the thing. If my brick is floating, or if my block is floating, what must be true about the weight of your object and the buoyant force? They must be equal, because it's not accelerating down or being accelerated upward. And so that means the mass of your fluid must equal the mass of your object. So when you are floating, the mass of your fluid that's displaced must equal the mass of your object. And that allows us to get rid of that. And therefore, the volume of my fluid to the volume of my object must equal the density of my object to the density of the fluid. And so what we can see from this is, if this is a fraction that is submerged, then this fraction is going to be less than 1. Right? Because the volume of my fluid that's displaced is equal to the green, and the volume of my object that's displaced is equal to the red. So the total volume of my object has to be larger than the volume submerged if my object is floating. So this ratio has to be less than 1. And that means the density of your object must be less than the density of your fluid. So this is the condition for floating. By extension, okay, this is less than. When your object is suspended in the fluid, that means their densities have to be equal. And if the buoyant force is larger and your object sinks, then the density of your object has to be larger than the density of your fluid. Okay? So this is a direct application for finding densities. Or likewise, if you know the ratio of the density beforehand, you can then predict what fraction of your object will be submerged, or be suspended, or will it sink? I should say, will it be suspended or will it sink? And if it floats, what fraction floats, right? What fraction is above the surface? Now, of course, one of the most common substances to use for these kinds of experiments is water, right? You use water for your fluid. But you don't have to use water. You could use oil, you could use honey, you could use molasses, you could use oil, you can use really, anything you would like. But the bottom line is that these will always be true. If you're trying to determine whether something will float in a given fluid, if you know what the density of your fluid and your object are, you can immediately then say whether it will float, whether it will be suspended, or whether it will sink. Now, let me note that in the case of suspension, okay, what will happen when you put the object in, it will sink until it is just suspended in the fluid, okay? It'll sink until the pressure differential forces equal the weight. And that doesn't happen until it's completely suspended if these densities are equal. But let's say I have a deep enough tank and I have an object that is suspended here so that the weight down and the buoyant force up are equal. What will happen is that object will stay suspended right there until I touch it. And then if I push downward on it, it will be pushed down and it will just continue downward at a constant velocity until it hits the bottom. Okay? Unless the tank is super duper deep and there's an extreme pressure change and the drag forces on it change. But otherwise, it will just sink through the fluid, especially through small tank sizes and so forth. Okay? So that's one special property about the suspended situation, okay? But that is Archimedes' principle, and up next is Bernoulli's principle.